This tutorial is brought to you by PE Prep Engine. Free study guides and practice questions at peprepengine.com.
Week 6, Lesson 4, Physical Properties of Materials and Selection. Back in Week 1, you built the stress-strain curve, the modulus, and strain energy. We do not repeat those. This lesson is everything around them, the property table you look up, hardness, and how it stands in for strength, toughness, and the selection ratios that let you pick the right material for a part. Choosing a material is matching its properties to the job. Concept 1. The property lookup. Selection begins at one handbook table. Modulus, density, thermal expansion, and Poisson's ratio listed by material. Steel is about 3 times stiffer than aluminum, while aluminum is roughly a third the weight. That trade is the heart of material selection. Notice what is missing. This table prints no strength column, so never read a yield or ultimate off it. Strength comes from the mechanical properties table or, for steel, from hardness. And the stress-strain curve itself is Week 1's Lesson 9. We build on it. We do not repeat it. Concept 2. Hardness proxies strength. Hardness is resistance to penetration. Press a known load, measure the dent. Hardenability is different. It is how deep the hardening reaches, shown by the Jominy end quench curve, where hardness falls with distance from the quenched end. A deep hardening alloy steel stays high across the bar. A shallow plain carbon steel drops off fast. The payoff is the hardness to strength conversion for plain carbon steel. Tensile strength is the Brinell number times 5, 15 below a hardness of 175, and times 490 above it. The result is in PSI, and it is a steel-only relation, not for non-ferrous metals. Concept 3. Toughness, fracture, and creep. Impact energy stands in for toughness the way hardness stood in for strength. The Charpy test measures the energy to fracture, and repeating it across temperature reveals the ductile to brittle transition, a plateau of tough behavior that collapses to brittle as it cools. Fracture toughness, K1C, is the stress intensity at which a crack runs. Geometry factor times stress times the root of pi times crack length, with the factor higher for an edge crack than an interior one. Creep is slow strain under load that climbs with stress and temperature. Fatigue is defined here, but its sizing criteria are the Goodman and Soderberg methods from Week 2, unchanged. Concept 4. 3 more printed families, survey level. Electrical properties. A capacitor holds charge equal to capacitance times voltage. A parallel plate scales as permittivity times area over gap, and resistivity is resistance times area over length. Composites follow a rule of mixtures. Weight each constituent by its volume fraction to get density and strength, with the modulus bounded between loading along the fibers and across them. And binary phase diagrams tell you which phases exist, their compositions, and their fractions through the lever rule. Know the reaction names: eutectic, eutectoid, paratectic. By what transforms into what. Concept 5. The selection ratios, and these you derive by dividing. When the exam gives you a strength target and a weight limit and asks which material, you are comparing specific properties. Specific strength is strength divided by density, strength per unit weight. Specific stiffness is modulus divided by density. Neither ratio is printed, so carry them in your head. The key insight: the strongest material is not automatically the choice. Steel outmuscles aluminum outright, but aluminum and magnesium often win per pound. Divide by density and compare. That is the entire move. Setup. A plain carbon steel part reads Brinell 200. We first turn that hardness into a tensile strength, then compare the steel against a 60 KSI aluminum rod for a weight-critical tension member. The densities come straight from the Handbook property table. The aluminum strength is given, since that table lists no strengths. The plan: convert the hardness, form specific strength for each material, and compare. Solve. Part 1. Hardness to strength. The Brinell number is 200, above the 175 threshold, so tensile strength is the hardness times 490, 98 KSI. Below the threshold, you would use 515 instead, and that flip at 175 is the classic trap. Solve. Part 2. Specific strength selection. Divide each strength by its density. The steel, at 98 ksi and its heavier density, gives about 3.5 times 10 to the fifth. The aluminum, 60 ksi but a third the weight, gives about 6.1 times 10 to the fifth. Multiply back to confirm each. The aluminum lands near 1.8 times the steel's specific strength. So despite being the weaker material outright, it is the better pick when weight matters. That inversion is exactly what these selection questions test. Traps. 5 ways this bites. 1. The hardness to strength branch flips at Brinell 175 times 515 below times 490 above. 2. That relation is plain carbon steel only, and it returns PSI. 3. The property table carries no strength column, never read a yield off it. 4. Specific strength and specific stiffness divide by density, not area, and the strongest material is not automatically the lightest for strength pick. 5. Keep hardness separate from hardenability, and for fracture toughness use the right geometry factor, 1.1 for an edge crack, 1 for an interior crack. Quick recall. Read stiffness, weight, and thermal growth off the property table, which carries no strength. Hardness proxies strength for plain carbon steel through the 515 and 490 relations, split at 175. Impact energy proxies toughness and marks the ductile to brittle transition. Fracture toughness sets the tolerable crack. Creep is slow strain under heat and load. Electrical, composite, and phase diagram relations round out the printed set. And the 2 selection ratios you derive by dividing specific strength and specific stiffness. Match the property to the job and pick on the ratio, not the raw number. Next up, Lesson 5. Manufacturing methods. You can now read a material's properties and select on them. The next question is how that material becomes a part. The handbook prints only heat treatment, annealing, normalizing, quenching, tempering, which reaches right back to today's hardenability curve. The other manufacturing families are not in the handbook, so we treat them as concepts to know and match each process to the job. Everything's at PEPrepEngine.com. Cheat sheet, work solution, and a quiz attached here. If the course helps, subscribe.
The full study guide with every equation and common exam trap is free at PEPrepEngine.com. Link in the description. Machine design, HVAC, structural, civil, and electrical series are coming soon. Subscribe so you don't miss them.